Hi everyone, this is Chandan and you are watching the learning field. So this is our lecture 4 of ordinary differential equation lecture series. So in the last video, we have discussed about the first order differential equation and existence and uniqueness of first order differential equation. Fine. In today's lecture, we will start actually the general theory of linear differential equation, and most importantly the concept of Wronskian. Fine. So stay tuned, and before starting I'm going to just tell you that those who are not subscribing my channel till now, so please do subscribe the channel. So this is the general form of a differential equation. So this is not the linear differential equation. So this is a very general form. This is not linear. Okay, this is not a linear differential equation. I'm just going to NA to the general differential equation. Sorry, first order. Actually, this is first order, and degree is n. So P1, P2, and Pn are functions of x and y both, where dy dx power m. So this is a first order nth degree differential equation. Fine. So this equation, what is the solution process of these types of equations actually? So one method is the equation solvable for p. So this one differential equation one, suppose, can be written as p minus f1xi, p minus f1xi, and p means dy dx, and so we can write this as a nth product of this, because the degree is n, and equating each factor equal to 0, we obtain the n equations, and then we solve this n equation one by one, because this is a first order differential equation, simple differential equation, that is dy dx plus py equal to q form. So this form, and this is very easy, we know that we can solve this by using the integrating factor method, and the solutions are these for these n functions. Now if we supercompose this types of things in this equation, so product of this n differential equation equal to 0. So this is the solution, and since the ODE 1 is of order 1, so there are cannot be more than one constant basically. So if we write these things, so c and c, this nc, suppose c1 into c2 and cn, this is actually the constant, and this is only one constant from this differential equation, because other c's are going with the variables. So only one constant term there will be remaining, that is this types of term. Then number 2 is equation solvable for x. So if f x y p means dy dx, this is equal to 0, this can be expressed as f equal to x equal to f of y into p function, then differential with respect to p, we get dx dy, and this is equal to 1 by p. So this is 1 by p in LHS. This is equal to any function, suppose phi of this function should be in y, p, and dp dy. Now we get a differential equation on this dp dy and p. So this is a first order differential equation in y, p, and c. We can easily solve this. Instead of this dx dy, we get a dp dy types of solution. Suppose here r star into y, this is equal to, suppose, any function of 0 maybe. So then solving and then putting the value p equal to dy dx, again we have to solve the same thing for the differential equation. Now eliminating p from 1 and 2 is not possible, so we solve 1 and 2 in to express x and y in terms of p and c. So x equal to f1 pc, y equal to f2 pc, and like so on. So or if there have actually, so these together forms the general solution. So this is one procedure to solve these types of equation. Next is equation solvable for y. If x y p is equal to 0, we can write if y equal to f y p. Actually this y equal to f x p, and in the above problem x equal to f y p, actually if we can express in differential equation, suppose x is explicitly present, or y explicitly present in that differential equation. So we can write in this form. Explicit means we can differ, means suppose there are x cube dy dx plus y is equal to suppose function c. So we can write it as y equal to something. So that means y equal to something means this is solvable for y. And similarly, if this reverse, that is we can write in x equal to something, then that is solvable for x. So we can write is p equal to phi xy dp dx. Let the solution be this one. Then eliminating p from 1 and 3, we get, this is equation number 1, we get the form g of xy c equal to 0. If elimination is not possible, we solve 1 and 3. F similar process, f c pc and y f2 pc. This together gives the general solution. So these are very basic thing. I think you all solve these types of problem in your graduation time. Solvable for x, solvable for y, and these are very basic. From here no questions make from CSIR, make in CSIR. Now another form is Clairaut's form that I forgot in the last lecture, which is y is equal to px plus fp. Then the solution is directly we can write y equal to cx plus f of c. Now classification of linear differential equation. Now that is the above equation is only the general first order differential equation. Now this is the linear differential equation of nth order. See, this is dy dx to the power n. That means this is a differential equation of order n. So a naught x, a1x and a(n)x, a(n minus 1x, a(n)x, this is equal to qx suppose. So if this qx equal to 0, then we call the differential equation is homogeneous, and if qx not equal to 0, then this differential equation is called non-homogeneous. Now there are two things, one is constant coefficient and one is variable coefficient. If these a1, a2, an minus 1 are constant for all I equal to 1 to n, then we call the differential equation, this linear differential equation is with constant coefficient. If these are variable in x, then we call the linear differential equation with variable coefficient. And procedure of these two types of equations are different. And we are not going to this solution part today in this video. In the next video we will go in these types of equations. Now what is principle of superposition? So principle of superposition is very important to solve linear differential equation. So consider the nth order differential equation, this one, the above differential equation 1. Let y1, y2 and yn up to yn are the n solutions of the above differential equation. Then the linear combination CIYI is also a solution of the above differential equation if qx equal to 0 or summation Ci equal to 1. So that is this summation Ci equal to 1 is known as what? This is known as convex combination. So that means for homogeneous differential equation, in case of homogeneous that is qx equal to 0, then summation CII, there is no condition on CIYI. All any combination will be solution. But in case of non-homogeneous, this combination should satisfy that summation CIYI equal to 1. That is, this is convex combination. Fine. There is no restriction for homogeneous, but restriction for non-homogeneous, and which is that the linear combination should be a convex combination. Fine. Now fundamental set of solution, let f1, f2, fn be the n linearly independent solution of an nth order linear differential equation. Then these solutions, that is set of functions f1, f2, fn, is called the fundamental set of solution. So this is very important. So the set of linearly independent solution is known as the fundamental set of solution for the differential equation. Now there are some results which are very important here. Result number 1 says that the solution set of nth order linear homogeneous ordinary differential equation forms a vector space. So this can be comes in the question paper as an option, you can say. Number 2 is the solution set of nth order linear homogeneous differential equation is a vector space of dimension n. So it forms a vector space and in n dimensional vector space actually. Number 3, the solution set of nth order linear homogeneous ordinary differential equation has exactly n linearly independent solution. Okay, so if there is an nth order linear differential equation, that means the dimension of solution space is n from this result, and there are n linearly independent solutions. That is, a set of n plus 1 solution must be linearly dependent. Number 4, the solution set of nth order linear non-homogeneous ordinary differential equation never forms a vector space. That is, the vector space only form in case of homogeneous. For non-homogeneous case, the vector space is not formed. Fine. Next, now we comes to the concept of WRONSKIAN. What is WRONSKIAN? This WRONSKIAN is very important concept for any exams. Consider nth order linear homogeneous ODE. Suppose this one, where a1, an, a1 to n and qx are continuous functions of x for some interval I. Let y1 to yn are n solutions of the above ODE. Then the WRONSKIAN of this n solution is defined as this determinant. WRONSKIAN a wx equal to y1, y2, yn up to y1 prime, y2 prime. These are the first order derivatives of yx. Then the next row will be second order derivative, and similarly up to n minus 1th order derivative. Okay, in the last row. So WRONSKIAN wx is always continuous and differentiable, but higher order derivatives may or may not be exist. Fine. Now basically in the exam paper we use second order, up to second order. There is questions comes from the WRONSKIAN up to second order. So consider this differential equation. A1, A2 are continuous functions of x and x1. X belongs to this interval. Now the WRONSKIAN is defined by wx equal to y1, y2, y2, y1 prime and y2 prime, where y1 and y2 are the solutions of the above ODE. Fine. Now wx is a solution of first order linear differential equation. This, hence the continuous and differentiable is given by this. So we can find the WRONSKIAN by using, if the differential equation is given, then this is the one shortcut formula which is known as the Abel's formula to find the WRONSKIAN. Fine. We comes to example after some important results. So these are very important results. See, let wx be the WRONSKIAN of y1 and y2. y1 and y2 are the solution of a second order linear homogeneous differential equation. That is w equal to y1, y2, y1 prime, y2 prime. Then number 1, if there exists x0 such that y1 x0 equal to y2 x0 equal to 0, that means y1 and y2 has a common 0, then what happened? This term goes to 0, this term goes to 0, that is complete determinant is 0, that means WRONSKIAN is 0. Therefore y1, y2 are linearly dependent. Fine. Number 2 is if y1 and then the contrapositive thing is of this above result 1. So if y1 and y2 are linearly independent, then there does not have a common 0 of y1 and y2. Okay. Number 3, if y1 and y2 have common point of extrema, if y1 and y2 has either common point of maxima or minima, that is extrema, that is if y1 prime equal to 0 and y2 prime equal to 0 for some point, same point x naught, then again happen this second row equal to 0. That means y1, y2 are linearly dependent. Next result number 4, if y1 and y2 are linearly independent, the contrapositive part, then there does not have a common extrema. Number 5, if x0 is repeated 0 of y1 or similarly y2, that is y1 x0 equal to 0 and y1 prime x0 equal to 0, common 0 means this is a second order 0, you can say 0 and 0 repeated 0. Then similarly for y2, WRONSKIAN equal to 0 and y1 and y2 are linearly dependent. Similarly, contrapositive of this is if y1 and y2 are linearly independent solution, then neither y1 nor y2 has repeated 0. Number 7 point is every non-trivial solution of y1 yi of second order linear differential equation only have simple zero, that is does not have a repeated zero. This also follows from the above result. Now I forget write to one. So what is that? A WRONSKIAN of any function wx is either 0 throughout the interval. This is very basic result and we all know that throughout any interval or never 0. That is basically, suppose if there exists, suppose x naught belongs to, suppose AB, it is an interval, and suppose WRONSKIAN of x naught equal to 0, then this implies WRONSKIAN of x for 1.0, this is equal to identically 0 for all x belongs to that suppose interval I. Fine. And if non-zero at any point, that means it is never 0. Fine. This is also very important result. Now if we take an example of this, so what is the formula to find the WRONSKIAN? So if we compare this as suppose a naught equal to x, a naught is a coefficient, a1 is the coefficient minus 2x square, and a2 is the coefficient of y, which is e to the power x. And for WRONSKIAN, using Abel's formula, wx equal to a into what is the WRONSKIAN? E to the power integration what? A1x by a naught x, a1 by a naught to dx, which is equal to a into e to the power minus 2x square by x dx. X is cancelled, 2x means e to the power a e to the power minus, minus 1 minus inside the bracket, so this is should be plus. In formula itself we have a minus, so e to the power 2x means x square by 2, and 2 into x square by 2 got cancelled. So this is the WRONSKIAN, this is our WRONSKIAN, wx equal to a e to the power x square. Now here the 4 values are given, all the points are 0, that means we have given WRONSKIAN at the point x equal to 0, which is equal to, if we calculate, then y1, we know that y1, y2, y1 prime, y2 prime, so this is equal to y1 means 1, 1 prime means 1, y1 it means minus 1, this is 1, this is 1 plus 1, this is equal to 2. See, if we get this function, this is equal to 0, then throughout the interval we can say this is 0, but this is non-zero, therefore we have to calculate this. And so mostly we write here, so w at 0, if we put x equal to 0, this is equal to a into e to the power 0 means 1, that is a equal to w at 0, so this is equal to 2, so we can write w at x, this is equal to 2 e to the power x square. Now if you can find, if you want to find at any point, suppose this is given, you have to find at x equal to 2, what is the value of WRONSKIAN at x equal to 2. So you can easily find from here, WRONSKIAN at w equal to 2 equal to 2 e to the power 4, or if any other point be given, suppose at x equal to half, what is the value? W half is equal to 2 e to the power 1 by 4, and so on. We can write, find the value of the WRONSKIAN at any point. And one more types of example given in the exam paper of CSIR NET. Suppose whatever may be the differential equation given, and you say you are given that w at suppose half at that point, this is equal to 0. Then what are the answer? What, suppose 4 options are given, that y and y2 are linearly dependent, and y1 and y2 are linearly independent. Number C is y1 and y2 have repeated 0. So if repeated 0, then the condition that is given, suppose y1 at any point, suppose 0, this y1 0 equal to given 0, and y1 prime 0 equal to also 0. So that means this condition imply what? Y1 at any point, suppose this is not 0, suppose this is 1 at 1. So that means y1 has repeated 0 at the point x equal to suppose 1. So at one point y1 has repeated 0. That means the value of the WRONSKIAN, if this is given, then WRONSKIAN value x throughout the interval, this is 0. Fine. And then what will happen? X, wx is y and y2 are linearly dependent. Maybe these types of option also included, that y1 has repeated 0. Suppose in the option C, that y1 has repeated 0 or zeros of order 2 or like something like that. Y2 has zeros of order 2. So these types of questions can be asked, generally asked in the CSIR NET or any other exam paper from the WRONSKIAN point of view. So this is the lecture. I end this lecture today here. In the next lecture we will discuss some analysis of zeros, which is very important for linear differential equation, and proceed further. Fine. So how was the video? If this video is helpful for you, then definitely give a like to this video, share it with your friends, and don't forget to subscribe the channel. Okay, thank you.